So we defined the heat and mass transport coefficient yesterday. So supposing if it's a flat plate, you have a boundary layer and you have fluid which is flowing past the object. What is H? What's H? Yeah? Yeah, heat transport. Okay, so it's flux which is minus K F dt by dy. So if this is y direction, evaluated at y equal to 0, okay. So that's the flux of heat that is transported at the boundary, at the interface, divided by the temperature difference, okay, bulk temperature difference. And similarly one could define mass transport coefficient as diffusivity multiplied by divided by Ca. Okay. So now let's go a little bit more and into the details of what is boundary layer and describe some of these processes and attempt to quantify them. Okay. So before we do that, we need to understand some of the flow properties, right. So remember that there is fluid which is flowing past this object. So therefore any transport process inside the boundary layer is going to be a strong function of the nature of the flow itself, okay. T dependent on X? Of course, yes, of course. So there are two classes of flow types called the laminar and turbulent flow. So there are two classes, these are the two different nature of flow of a fluid. Laminar flow is it's an ordered flow where things flow in streamlines, and turbulent flow is where there is fluctuations and there is cross mixing of fluid particles, and so there is no streamline flow, okay. So laminar flow is essentially a streamline flow, while there is vigorous mixing of fluid particles in the turbulent regime. So any fluid flow you can have either laminar or turbulent, and somewhere in between is the transition region. Okay. So now what's the characterizing number which tells you whether it is laminar or turbulent? It's called the Reynolds number, okay. Now what's the Reynolds number range for a flat plate where you will have laminar flow? Yeah, up to what Reynolds number is the flow of laminar? 2100. That's for which system? That's for pipe flow. This is not pipe. That's for flow through a tube, right? That's for pipe flow. What is it for flat plate? So it's 10 power 5. So the length at which the Reynolds number reaches 10 power 5 is actually the limit for laminar flow regime, okay. And for turbulent flow, so anything less than 10 power 5 it's laminar. So note that in pipe flow, which you have already studied, the characteristic length scale is the diameter of the pipe. Here the characteristic length scale is the length up to which from the leading edge of the plate, okay. So if you have a plate here, so this is x equal to 0 and this is x equal to some L. So the length of the location from the starting point, that is x equal to 0 of the plate, so that's the length scale that you should use for defining the Reynolds number. So that tells you which location along this plate the flow is laminar and which location it is turbulent. Okay. So typically 3 into 10 power 6, that's turbulent regime. Okay, and anywhere in between is it's called intermediate regime. Okay, so it's neither laminar nor turbulent. So anywhere in between, it's called transition regime. So you can see features of both laminar and turbulent flow in this region here. Okay, so now supposing I stare at the heat transport coefficient expression. Okay, now what can we say about the gradient as a function of, so when you go into the flat plate, you expect the gradient to decrease or increase? What do you expect? Yeah, decrease or increase? Why? Okay, so the residence of or the contact time of the fluid with the flat plate increases as the fluid particles are actually traversing through these flat plates, right, flowing past it. Therefore, you would expect that the fluid would have gained more heat from the flat plate, and therefore you would expect that the gradient will actually decrease when you when you go further into the flat plate. So this is the gradient at x equal to but y equal to 0. So we can sketch it. Okay. So if that's the profile at, let's say, this location x1, okay, some other location, because the fluid is now exposed to the plate for a longer period of time, more heat would have got transported. So you would expect that the profile would look something like this, where the gradient has now decreased because the fluid particles which are actually, let's say, well above y equal to 0 would also reach temperatures which is close to the plate temperature. So therefore you expect that the gradient would decrease as you go into the plate, and that simply means that the heat transport coefficient would actually increase as you, this directly translates into the reduction in the heat transport coefficient. Note that this is local heat transport coefficient. There is a reduction in the local heat transport coefficient as you actually go into the plate. Okay. So Ts and T infinity are measurable quantities, and we can assume they are constants, and Kf is an intrinsic conductivity of the fluid, it's an intrinsic property, and we can assume that also as a constant. So clearly the heat transport coefficient, the nature of local heat transport coefficient depends primarily on the temperature gradient at y equal to 0. Okay. So the whole of this exercise that we are going to do in convection topic is essentially to find out for various kinds of system what is this temperature gradient. So all the quantification process that we are going to actually discuss in the next several lectures for various kinds of geometries, various kinds of flow properties is essentially to find what is this gradient. If we know this gradient, we are done, because this is a definition of heat transport coefficient, and a similar way for mass transport, if we know the concentration gradient at y equal to 0, we are done. Okay. So in principle, the momentum, heat and mass transport, they can in principle occur simultaneously. Okay. So there could be a system where you have a boundary which is maintained at a higher temperature than the fluid which is flowing past it, and there could be some species which is simultaneously moving from the solid phase to the fluid phase. It could be like a membrane, for example. Okay. An excellent example of that is the cholesterol which actually deposits into the arteries of the blood system, right? So of the blood circulation system. So the blood actually carries cholesterol. So whatever food that we eat, it's processed in the the nutrients are extracted in the intestine, the small and the large intestine. And so the way the nutrients are carried is the bloodstream, they actually go there and then they carry the nutrients, and these nutrients are now circulated in the bloodstream. So whatever cholesterol particles or fat material that you eat, whichever is absorbed by the intestine, it's actually circulated into the bloodstream, and then these they go and deposit in the arteries. Now you could, it's a reverse process of what we saw here, where the concentration in the solid phase is higher and the liquid phase is lower in the example that we had considered. But in the deposition of cholesterol, the cholesterol concentration will be higher in the fluid stream, and you have deposition of cholesterol on the surface. Okay, so it's a very, very strong application of some of the things that we are going to see, and in fact people have actually found out what is the mass transport coefficient for cholesterol deposition, and that has a strong implication on a perfect diagnosis based on the concentration of cholesterol in the blood. See, this is a very difficult thing to see, one cannot see how much cholesterol is being deposited in the artery. There is no in situ way of doing that. Well, there are some ways now, but there is no clean way to do it. So if we can find out what is the approximate mass transport coefficient, and based on the concentrations, we should be able to estimate the rate at which the cholesterol is being deposited in the arteries. So this has strong implications in deciding the medical strategies, or what kind of invasive treatment that one has to have if there is a strong cholesterol deposition. Okay, so there is a lot of applications for some of the things that we have seen, and in fact it depends on temperature. You put your hand in front of the infrared camera, you will see that the temperature of different locations is different, and that's true for the bloodstream also. So the local temperature of different locations of the body will be different. So it will be like a simultaneous heat, mass and momentum transport, all three are occurring simultaneously. So it's a very, very important aspect. So it's a simultaneous momentum, heat and mass transport. So in most real systems you will see that it occurs simultaneously. So supposing if you have an arbitrary object, okay, where there is a fluid which is flowing past this object. Okay. Now if I define V as the upstream velocity, okay, so note that I am going to introduce some key definitions. So V is the upstream velocity. So this is the velocity of the fluid before it sees the object. Okay. Then when it sees the object, obviously you are going to have a boundary layer, a velocity boundary layer or a momentum boundary layer. So let us say that this is the velocity boundary layer. Okay, so it could be in all three dimensions. So I put an x bar for vectorial representation, and one could have a concentration boundary layer, and one could have a thermal boundary layer. Okay, so all three will exist simultaneously when there is a fluid which is flowing past an object, and there is heat and mass transport which is occurring simultaneously. Okay, so the thermal boundary layer thickness, okay, is actually larger than the concentration boundary layer thickness, and that is larger than the momentum boundary layer thickness. In fact, mostly not today's lecture, maybe in the next lecture or the one after that, we will actually show rigorously that this is true. So right now you assume that the thermal boundary layer thickness is larger than the concentration boundary layer, and that is larger than the momentum boundary layer. We will actually show this later. Will be shown later as to why that's the case. In fact, the governing equations will fall out from the governing equations that this is really the case. Okay. All right. So now the question is, how do we quantify this process? How to quantify this process. So note that the objective of the course is to quantify these different heat and mass transport processes. So if they are occurring simultaneously, how to quantify them? How do we find, when I say quantify, what I mean is, what do I mean? What did we mean by saying quantification when it came to conduction? Yeah? You wrote the governing equation, get the temperature profile. So when you say quantify, you need the temperature profile as a function of x and y, and you need the concentration profile as a function of x and y, and you need the velocity profile as a function of x and y, and you have two components. If it's a 2D system, you have two velocity components u and v, right? So it's the x component velocity and v is the y component velocity. So if we know all of these, then we are done, because the objective is to find dt by dy. That's what we need to find. We need to find dt by dy. This will give you the heat transport coefficient, dCA by dy at y equal to 0, that will give you the mass transport coefficient, and du by dy, what does this give? Du by dy at y equal to 0, yeah, what does it give? Coefficient of viscosity? No, it's not coefficient of viscosity. Shear stress. It gives you the friction coefficient. We defined this in yesterday's lecture, okay. So if you know these three gradients, you have actually quantified or you have identified the characteristic properties of the three boundary layers, which means that we have identified the characteristic properties of the three transport processes that are occurring simultaneously, okay. So in order to find these, we need to write for u and v, we need to write the x momentum balance, we need to write the y momentum balance, we need to write the energy balance, and we need to write the mass balance. So these are the four balances that we have to write, and of course continuity equation has to be satisfied. Okay. So these are the 5 different pieces that we have to write. So that will essentially, these are the equations which will capture the profiles of temperature, concentration and velocity. Okay. Okay. So suppose I assume that it's a steady state process. I assume that it's a steady state process, and if I assume that the properties are constant, this is not a bad assumption to make. If I assume that the properties are constant, and if I assume it to be an incompressible fluid, okay. So we will not deal with compressible fluids in this course. There is an advanced transport course, so some issues related to compressible fluids and quantification of compressible fluid systems would be dealt with in that course. So this course we will assume that all the fluid is incompressible, okay. Alright, so we need to write the x momentum balance. So what are all the processes which are likely to occur? So remember that whenever you write balances, you must identify the individual processes which are occurring in that problem, and then you find out what is the mathematical representation and then put the correct signs to it, you're done, okay. Of course you can do it by writing shell balances, that's the rigorous way of doing it, but you must also know what is a non-rigorous way, otherwise you don't know if you made a mistake in your shell balance. So you must also know what is a non-rigorous way of doing it, okay. So what are the different processes which are occurring here? Let's say in momentum balance. Shear stress, okay. So that's the, why only wall? It's only at the wall. So there can be shear stress between different fluid elements, right? So in general, shear stress, okay. What's the mathematical representation of shear stress? Mu into del square, okay. So it will be del square u if it is an x component momentum balance. So note that u is the x component velocity, u is the x component velocity and v is the y component velocity, okay. What else? Pressure gradient, okay, because it's a forced system, you are pumping fluid, you are actually pumping the fluid to flow past the object, so there has to be a pressure gradient, otherwise there is no flow, right. So if pressure gradient is 0, there is no flow, okay. What else? Yes, gravity forces. So in classical literature it's called body forces, okay. So all gravity etc. will be coupled into body forces, okay. What else? You may not have heard this term, but it's what that's what it's called as, it's called body forces. What else? What's missing? I mean you have seen Navier-Stokes equation, right? Yeah? Convective momentum, okay. So you have a convection, right. So it's essentially different terms what you would see in your Navier-Stokes equation that you have studied, right. So if we put them all together, what's the mathematical representation of momentum, convective momentum term? Rho VV, so that will be rho into, if I open it up, dou u by dou x plus v into dou u by dou y. So that's the momentum in the x direction, that's the momentum in the y direction, okay, and that should be equal to the pressure forces, so that will be minus dp by dx, okay, plus the shear term, it will be mu into del square u plus whatever body forces. So x dot is the body forces, okay. One can actually get the same expression by starting from Navier-Stokes. You can actually start from shell balances. I mean in Navier-Stokes anyway you can get from shell balances. So you can start from shell balances and put the right approximations and you will see that you will get this. You can start from Navier-Stokes, you impose the approximations or assumptions, you should still get the same expression. And the third way is you simply identify different processes which are involved, what is the mathematical expression corresponding to that and put the correct sign. Because you know what is happening, okay. So this is the, supposing the fluid is moving in this direction, okay. So if I take this direction as positive, okay. So convection is taking the fluid from x equal to 0 to x equal to L, right. So that's what, let's say if this is my positive term here and dp by dx has to be exactly. So moment you know what is your positive direction, everything else falls into place. What is the purpose of shear stress? It's going to retard the flow, right, because there's going to be friction between fluid layers and that's why the shear stress comes here and body forces will come on the other side. It's very easy to put this. So a good exercise would be to go back to Navier-Stokes equation that was derived to you in transport course and stare at it and see what are the different terms and how does the sign actually forces the different terms to come in different locations in the equation. That will help you to identify what should be the sign that you should put for each of these terms, okay. So you must actually convince yourself that there are different signs that you have to put based on what are the different processes. In fact, if you look at the shell balances, the sign actually falls out naturally because you would have accounted the signs when you wrote the shell balance, right? And you must convince yourself what these signs are. It's very, very important, okay? So this is a quick way of writing the balance. Of course, the laborious way is to write the shell balances, and the intermediate way is to start from Navier-Stokes, okay? Alright, so this is the x component momentum balance. Similarly, we can write the y component momentum balance. It will be rho u dv by dx plus v dv by dy, that is equal to minus the pressure gradient in y direction plus mu del square v plus y dot. So, if I assume y dot is the body force in y direction, so that is the y component momentum balance.